Hello everyone, welcome to this channel. Please subscribe, share and comment the video lectures. So today we will see about the first chapter of numerical analysis, which is about error analysis. So numerical analysis is just a branch of mathematics which studies about the methods and algorithms that are used for solving different problems in different areas, such as in mathematics, physics, computer science, medicine, social science, and other life science areas. So numerical techniques are widely used by many scientists, so that analytical solutions are certain limitations in practical applications. Sometimes exact solutions are not possible. So in that case, the major advantage of the numerical technique is that numerical answer can be obtained even though the problem has no analytical solution. However, the results from numerical analysis are approximations, and these approximation solutions are made as accurate as possible. And the reliability of the numerical methods results are dependent on the error estimate or bound. So that it's good to see the analysis of error and source of error numerical methods is a critically an important part in studying the numerical techniques. So the main purpose of numerical analysis, as we have said before, and scientific computing is that to develop an efficient and accurate method, the more fastest convergent technique to compute a given approximate solution to the given quantities that are difficult or impossible to obtain its analytical solutions. So let's see, in numerical analysis, there are two types of numbers. These numbers are exact and approximate numbers, and an exact number is a number that represents exact number that represents itself, and within the exact number, no uncertainty is associated with it, and there is no approximation is taken from the exact number. So such numbers like 5, 21 over 6, 12 over 3, 4.5, 2, 0, 3 are exact numbers, and those type of numbers are approximate numbers, and sometimes numbers which cannot be, there are numbers which cannot be expressed by a finite number of digits, so that for a practical computation, we should manage those numbers, so that numbers which represent the exact number with a certain degree of accuracy are said to be an approximate numbers. For instance, radical 2, which is 1.41421, which is an intermitting, E, which is 2.7183, which is an intermitting, are not exact numbers since they contain infinitely many digits. Therefore, numbers obtained by rooting or lifting a few digits from the exact number are called approximate numbers. So 3.142, which is an approximate representation of pi, and 2.718 is also an approximate value of E, an approximate value of E. So when we are using such numbers in practical computation, we are going to approximate to a manageable size. So that representation is said to be an approximate number. The other concept is about significant figures. Significant figures are digits that are used to express a given number. And digits from 1 to 9 are significant figures, and 0 is also a significant figure, but sometimes it's not a significant figure when it's used to fix the decimal point or fill the place of unknown or discarded digit. For example, you can see the number 5,879, 3.487, and 0.47262 contains for significant figures. Numbers such as 0.00486, 0.00038, and 0.00036 contains 3 significant figures. The zeros are used to fix on the place of the decimal. in the number here, the first four zeros are not significant figures, but the other two zeros are significant figures. The other one is a rounding of a number. So when we divide 2 by 7, we get an intermediate decimal fraction, which is 0.285714, which is it continues like that, which is non-terminating. So for using such a number in practical computation, it should be cut off to a manageable size, such as 0.28 in 2 significant figure, 0.286 in 3 significant figure, 0.2857 in 4 significant figure in CC. So the process of cutting off superfluous digits or removing superfluous digits and retaining as many digits as desired is known as rounding off. Or we can say that the process of dropping unwanted digits is said to be rounding off. So how can there are procedures to round off a given number? So numbers are round off according to the following code. So to round off the number of which has n significant figures into n significant figure, so discard all digits to the right of the nth place, and if the discarded number is less than 5, the first case, when the discarded number is less than 5 in the nth one, n plus 1's place, then leave the nth digit unchanged. So for instance, 8.893, when you want to round off to 3 significant figure, it is 8.89 because 3 is the third place, this one, then the third place is less than 5. When the n1 plus the n plus 1's place is greater than 5, increase the nth digit by 1. Increase the nth digit by 1. For instance, 5.3456. When we are approximate to 4 significant figure or 3 decimal place, which is 5.346. You can see that 6 is greater than 5, so that we add 1 on the nth place, so that it becomes 5.346. And when the nth plus 1 place is exactly 5, increase the nth digit by unity if it's an odd number, otherwise leave it as unchanged. For instance, 11.675. When we are approximated so to decimal place, 11.68. So clearly you can you can see that 7 is an odd number, and the n plus 1 place is 5, which is so if the nth place is an odd number, we add 1, so that it becomes 11.68 and 11.685. And you can, if you want to approximate to the 2 decimal place, then you can see that 8 is an even number, so that we leave as it is when we are approximate to 2 decimal places. So it becomes 11. Error analysis. So in any numerical computation, we produce an error. In general, we can say that error is a difference between the true value and its approximate value, and we can take it as like this one. Error is the true value minus its approximate value. So before going to see different type of errors, let's see what are the sources of error. So numerical results are affected by many types of errors. Some of the source of errors are error in a given input data. So the input data can be a result of measurements which have been contaminated by different type of errors. Maybe measuring instruments, different factors that affect that produce an error. The other one is rounding of errors during computation. So rounding of error occurs whenever an irrational number or a non-terminating decimal fraction is used for practical computation. We are going to round off the error, so that in such case we produce an error. The other one is truncation error. Truncation error occurs, for example, when an infinite series is broken off to finite terms, and when a nonlinear function is approximate with a linear one, so we produce an error. And the fourth source of error is implications in mathematical models. So clearly we can see that mathematical models are representation of a real phenomena, so that when we are representing the real phenomena, we cannot express exactly with an equation, so that we use simplifications, so that so that simplification produces an error. And the last source of error is human errors and machine errors. Humans produce by themselves an error, and the machine itself produces an error where we are computing when we are computing while going to analyze the given problem. Generally, errors may be divided into the following different type of sources. The first one is an inherent error. An inherent error is an error which is already present in the statement of the problem before we compute its solution. So inherent errors arise either due to simplified assumption in the mathematical formulation of a problem, or due to the physical measurement of the parameters of the problem. And these inherent errors can be minimized by obtaining better data and by using high precision computing aids in evaluating the data. The other one is round of error. Clearly, round of error is a quantity which arises due to the process of rounding of a number, and this rounding of error can be reduced by carrying computation with more significant figures at each computation step. And the third type is truncation error. This type of error is caused by using approximate formula in computation or replacing an infinite series by a finite one. And this when a function is, for instance, the series when we are truncating to a finite stage, then that after that term it will be an error. So if we take this function e raised to x, which is equal to represented by 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the power 4 over 4 factorial plus n. When we replace this one with in computation with a finite one, with 1 plus x squared over 2 factorial plus x cubed over 3 factorial, which as an approximate value of this one, then the truncation error will be the exact one minus the approximate one. It will be x to the power 4 over 4 factorial plus x to the power 5 over 5 factorial plus x to the power 6 over 6 factorial will be taken as the truncation error in computation. The other types of errors are absolute error, relative error, and percentage errors. Absolute error is clearly the difference between the numerical difference between true value and its approximate value. Numerical difference means the absolute difference of the error itself, the absolute value difference of the true value. The minus its exact value minus its approximate value. So it's an approximate error is the absolute value of the error, which is x exact value minus x approximate value, and the unit of exact the absolute error is the unit of the is the unit of the exact value. And the other one is a relative error, is the error which is obtained by dividing the absolute error with the exact value, So the relative error is defined as like this one. The absolute error over its exact value, and unit of the relative error is independent of it. It has independent, and the percentage errors is multiplying the relative error by 100 so that it's represented by this one. It's represented by this one. Similarly, like relative errors, the percentage errors are also independent of units. Let's see an example. Find the absolute percentage in relative error of if we round off 3 decimal digits given when we are rounding off x to 3 decimal places. When we are rounding off to 3 decimal, which x is equal to 0.005998. So when you round off this one to 3 decimal place, an approximate value will be 0.006 3 decimal place, or one significant figure. So therefore, error is a true value minus its approximate value. So this one will gives 0.005998 minus 0.006, which gives negative 0.000002. So the absolute error will be the numerical value, which is or the absolute value of the error. So it becomes positive 0.000002. So the relative error will be the absolute error over its exact value. So it will be 0.000002 over 0.005998. So it becomes 0.00333344. And the percentage error is the percentage error is 100 times its relative error, so that it becomes 0.3344. In the second example is round of the number 75462, which is 75,426 to 4 significant figures, digits, and then calculate the absolute relative and percentage. So after rounding of the number 75462, you will get 75,460. Therefore, the absolute error is the exact value minus its approximate value, and you get 2. It's an absolute error, and the relative error is the exact value, the absolute error over its exact value. So it becomes 0.0000265, and the percentage error is 100 times the relative error. It becomes 0.00265. And the third example is 3 approximate values of 1 over 3 is given, which is 0.30, 0.33, 0.34. Which of these 3 approximations is the best? So to find the best approximation, we compare the absolute errors. The number which has least absolute error gives a best approximation. Therefore, true value is 1 over 3, which is 0.3333, and infinity. Then the approximate value is xa. The first approximate value is x approximate 0.3. So the absolute error will be x minus x approximate, which is 0.3333 minus 0.30. So you will get 0.03333. When we take the second approximation, which is 0.33, the absolute error given by x minus x approximate, so it becomes 0.00333. And the third approximate value is 0.34. The absolute error given by x minus x is, which is 0.3333 minus 0.34, which is 0.00667. Hence, which one is the least one? You can see that 0.0333, 0.0033, and 0.00667. So you can clearly see that 0.00033 is the best approximation. So that 0.33 is the best approximation to the given number. So the other remark is if we approximate, if x is an approximate value of x correctly round off to n decimal places, then x minus x approximate is always less than or equal to 1 over 2 times 10 raised to minus n. So if x is equal to 8 over 9 and the exact decimal representation of x is 0.888, find the absolute error using an approximate rule when it is round off to 3 decimal places. So what would be its approximate value when it's round off 3 decimal places? So we have x is equal to 8 over 9, and we are going to approximate to 3 decimal places. So the decimal representation of x round off to 3 decimal places is x equal to 0.889. Then x approximate its absolute error is 8 over 9 minus 0.889, which is 8 over 9 minus 889 over 1,000. So when you are solving this one, which is the absolute value of minus 1 over 9,000, so which is always less than or equal to 1 over 2 times 10 raised to minus 3. Therefore, the absolute error is always less than or equal to 1 over 2 times 10 raised to minus 3. So in the next class, we're going to see the general formula for an error inverse problem and the series approximation, the errors in series approximations. So thank you for today.